Hi, my name is Vahan Davudyan. I'm a physics experimentalist, and today we're talking about the theory of separation of charges by Vahan Davudyan, physics experimentalist, and this is my email, vahandavudyan@aol.com. My inspiration came from nature. It was Platte River in Denver, Colorado. I will explain everything. First of all, I'd like to thank so many people, like physics lovers, science lovers, enthusiasts. They emailed me. That was so rewarding, and that's the way, that encouragement helped me to do more videos. I appreciate that. And then at the same time, I'd like to thank YouTube, which is an amazing corporation. It's like a huge network. It's helping so many people like me or the other science lovers to, to upload their videos. So we learn from one another, and then we exchange views, we communicate, and this is the way the YouTube is promoting science. And as a matter of fact, I just compared YouTube to synapse in a human's brain, which is comparing billions of neurons together. When we started with YouTube, it helped me a lot because most people watch the YouTube, and we appreciate that they do a good job. It's amazing. I have no idea what we could do. What could we do without the YouTube? I have to explain something. I started by year 2000, and then I finished the theory of separation of charges. But I had to finish this by year 2004 because, like I said, my inspiration came from Platte River in Denver, Colorado. I will explain in a minute. But what happened? We have only like 26 minutes in my videos, which is called positive and negative charges. You can watch. I uploaded that a year ago, but unfortunately 2 DVDs were lost or damaged, and I have no idea what happened. I was so lucky I had the photocopies, and those days 2004, there was no YouTube, so I had to pay thousands of dollars for the website, and then the photocopy, and then for DVD and everything else. And I had no choice. I had to type in everything on 11/17. It was so strenuous, so difficult, but I did all my theories, and I'm glad I had the photocopies. And then I realized this is the best time. I have to just do those. The reason why I didn't have this Gauss meter, I had this Gauss meter, which is an amazing device. It's a DC Gauss meter. It can measure up to 10,000 Gauss, which is the measure of magnetism in DC. And then it's so important. I will show you how important this is, and it helped me a lot. So I had no choice, and then I had to get those photocopies and then notarize them, and then take it to notary public, and then I had to copyright them. It was so difficult. And finally I decided to get those photocopies and then recreate everything, and then I will explain everything now. So I'm glad this is worked out fine for me, because without the photocopy I had no idea. I'm talking about exactly 20 years ago. I did not forget what I did on my experiment, but because I had the photocopies, it'll be precisely exactly what happened in 2004, and then I will explain it. So this is what happened in Denver, Colorado. Let me just post this poster so you can see. This is called the Confluence Park. This is the downtown Denver, and this is the bridge we used to walk here. There's a park over here, and then you can take a walk, or you can take your dog, and then there's so many beverages you can have here, so many entertainment here. So one day, it was 2004, and it was July, and you can see how calm the water is, how blue it is. So I was here on this bridge, and all of a sudden something caught my attention. And I don't know what happened. Unintentionally, when I looked down this river, I realized, when the water is flowing here, that wood chips and everything else, like floating particles, from my perspective, they were going clockwise, from the other side, they were going counterclockwise. And immediately I was inspired that, flow of river is like a flow of electrons or flow of current, and then this is going to be S and this is going to be N, or in other words, positive and negatives. So I wasn't sure about this, so I had to go home and then buy some wood chips or dust bark, and then I went up the stream like half a mile, so I had to spread that in water. And when I came back here and then I stood over here, from my perspective, this side was going clockwise and this side was going counterclockwise, and my guess was 100% right. So I had to go home, and this was great inspiration for me. And then I knew that something is happening. The reason why, I saw a very good experiment by Andre Ampere, which was one of the greatest scientists at the time. And then he did famous experiment, and then he had two wires, and then when they, well, of course I don't have that experiment, but I can show you. He had two current carrying wires like this. When the current goes in the same direction, they attract each other. When one of them is going to the opposite direction, they repel each other. This became kind of prime obsession for me, mystery. I said, well, why? Well, of course, I have so many physics books, real good physics books, and then I used to buy them from Barnes & Noble. They are so comprehensive, so good. God knows I checked so many physics books, there was no explanation what happened in microscopic level. But I knew that something is happening, and my guess was right. I knew that the charges are separated. When we have that flow of current, exactly the way I did this in this river, that river is causing these wood chips to go from right side and the left side, or clockwise and the counterclockwise. And this was great idea. This was one of the best day in my life, because I discovered something amazing. When I went home, and then I realized that I have to do so many experiments so I can prove my point. And I don't know what happened. I was sitting in my balcony, and all of a sudden something inspired to me. I said, Vahan, if Mr. Andre Ampere did the experiment, what will happen if I bend the wire like this? So if the charges are separated, so what will happen? So we have S facing S, or we have N facing N. So practically they should repel each other. I wasn't sure. When I came home, I had to do this experiment, and my guess was 100% right. So I had to suspend two copper wires, and then I had to short them with 12 volts, and then I realized my guess was 100% right. It was 100%, because when we have like S is facing S, because of separation of charges, what happened? They repel each other. Anyway, I show you in a minute, but I have to explain something before I show my experiment. And this is amazing device. This is called a scanning tunneling microscope. Let me put this up, you can see. This solved so many things in science, and as a matter of fact, this was breakthrough in science. And you can see Mr. Heinrich Royer and Gerd Binning, they got Nobel Prize in IBM lab in 1986, and this was amazing idea, the way they did it. And before this, microscope doesn't show everything, but when you watch Science Channel, you can see how important this scanning tunneling microscope is. Well, of course, there's so many things, explanation. I'm not going to go through it because it's time and so many things. And this called piezoelectric. In Latin means, touching something. So, but what they did is amazing. And this also helped me a lot. And then I remember when I studied these two scientists, I realized they discovered something amazing. They said in 1 millimeter, which is so little, I can't even show you now. Probably this is less than 1 millimeter, this wire. In 1 millimeter, 1 millimeter, we have 1 billion dipoles. Well, what do we mean by dipoles? My whole theory is based on dipoles. And can you imagine, we're talking about nanometer. 1 billion is a nanometer in 1 millimeter of wire. So what happened in a microscopic level, and that is what happened. And then charges are separated due to the, dipoles. Dipoles are exactly microscopic, and like I said, they're nanometers, and then one side is a positive charge and the other side is a negative charge, and they are opposite each other. They're exactly the same, equal. But what happened, there are billions of dipoles in this maybe 20 centimeters wire. But this is another poster I show you. What this scanning tunneling microscope did was beyond my imagination. How important this is in our life, in science. And we owe it to Mr. Gerd Benning and Heinrich Schroer. Well, of course, you can see here, this is the single zigzag chain of cesium atom, which is alkali metal. Well, of course, in a computer, they have to do some paints and everything else. Can you see that? That is beyond my imagination. What this, a scanning tunneling microscope does, this is 7 nanometer. Well, as you know, the one atom is practically 1 nanometer. This is 7 nanometer by 7 nanometer. You can see showing the atom. Isn't this amazing? How could we do without this scanning tunneling microscope? Now I'm going to have to show you my experiment because I have a lot and then I don't want to waste a lot of time. So I will start my experiment. So let me take these posters off so we can have more space here so I can show my experiment. This is my first experiment, and it's just so simple. I show you. So if you remember a few minutes ago, I said, if you bend the wire, what happened due to the separation of charges, it doesn't matter how we bend it from this side or the other side, it doesn't matter. So these are copper wires. Let me just put them in a row like this and then connect it to 12 volt DC. So I have 12 volt DC here. And by the way, I'm using the flow of electrons from minus to plus because I know the conventional is from positive to negative, but always my frame of reference is going to be from negative to positive. So you can see what happened. When I short this, see what happened, they should repel each other. The reason why I could not bend this solid wire, so I had to get something else here, so they will be more flexible, and then you can see, if I bring this close, see what happened. When I turn this on, let me see. See what happened? It's deflecting. So in other words, it's repelling that. So I had to do this experiment also with copper plates and aluminum. It doesn't matter. So it doesn't matter. See, these are two coppers, and then the same thing is going to happen here. Why? Because it doesn't matter. Charges are separated. If I get this copper plate, which is like maybe 2 centimeters by 10 centimeters, always we have S on this side and then N on the other side. Well, I'll show you in a minute with the Gauss meter and everything else. But let me show you this experiment first. So because they both have the same charges, they should repel each other. So this goes to the positive. Okay, that goes to the positive charge. So, yeah, this goes to the positive charge. And then the negative, I can go ahead and short it so I don't need, okay. So many wires here. So that one is the positive. Get this out of the way. And this one is the negative. Okay. If I short this, so see what happened, they should repel each other. So I had to put a little bit tape on this so they won't short each other. So So now I'm going to short this, see what happened. Did you see what happened? They repel each other. So now I start with the wires and then I will explain exactly how they work. Okay. Well, let me set this aside. This experiment is extremely important because this was the, most important experiment I started first, and then you can see, and like I said, my frame of reference is always from negative to positive. Okay. So you can see I have a copper wire here, and then this part is negative, and the other side is the positive side. So I had to use Gauss meter. Let me turn this on, you can see. This is amazing device. It measures the magnetic field, it measures the polarity, and then it shows everything. And I had to also use neodymium. This is the most important magnet or most powerful magnet in the world. Say neodymium, this is 1.5 by 1.5 centimeter. You may not believe this. This is 4,000 Gauss. If I measure it, I'll show you in a minute. So I had to use neodymium, I had to use compass and everything else. Now if I connect this to the 12 volt DC, you can see what happened here. Let me show you. So this is going to be the positive. This is going to be the negative, I'm sorry. This is going to be the negative. And the other one is going to be the positive. So when I connect this to 12 volt DC, you can see, well, of course I have to put this compasses here so you can also see the compasses. Okay. First of all, I'm going to show you with the neodymium. So I marked this S and N, so see how big they are, you can tell. So practically when the wire is connected like this is a copper wire. Well, of course I will show you in a minute. I had zinc, I had aluminum, I had silver, I had even lead. I'll show you in a minute. It doesn't matter, it always does the same thing. So when I connect this to 12 volts, you can see this was my guess that the charges are separated. Well, this wire is almost like, I would say, 1 millimeter thick, but it doesn't matter how thick or hard, thin the wire is going to act the same. So when I hold this over here, let me show you. and I hold this over here like this. See, because this is facing N, facing S, so there must be attraction here, see? Did you see what happened? But if I turn this around, so there must be repulsion. We turn this around. See what happened? It's repulsion. And this is amazing. I check them again and again and again. Always, this side or the side toward the wall is going counterclockwise and the other side goes clockwise. Let me turn this on one more time. See, you can see the compasses, well, of course they must be a little bit away. See the compasses? They're the same thing. Of course, I have to show you with the Gauss also. So this Gauss meter shows exactly. It shows minus for the N and it shows plus for the... Even a wire like this has the, Gauss meter shows. It depends on how thick the wire is and how much current goes through. But by experience, I know that this is going to be almost like 20 Gauss. So let me show you. So when I measure this part, so this is the probe, you can see. I'm hoping that you can see it over here because this is so little, maybe you can not see that. Let me turn this on. Wow, it's showing 24 Gauss. Okay, it was S on this side, and then let's see on this side, it's going only 10. So like I said, this was important experiment for me, because that is the way it shows why the wire has north and south. Well, of course, I have more experiment, and then I will show you. Let me set this aside. We have more than maybe 20 experiments. Okay. It's hard to detach this. Okay. This experiment is extremely important. I show you why. So now I have to turn this around. So always the minus is from my left side and the plus is the opposite side. So let me connect this also. So this is going to be positive. And this is going to be negative. Let's see what the negative. Right here. It's the positive. It's the negative. Oh, negative is here, right there. Okay. I have to explain about the dipoles. It's so amazing. I show you here with this wire. Whenever we have a wire like this, the one I showed you a few minutes ago, it's not going to do any work. The reason why, charges are separated. You go kilometers by kilometers, it's not going to do anything. What the great scientists like Michael Faraday and Andre Ampere, what they did, and I don't know why it was a coincidence or why, both of them used the same one loop. This is called loop. Well, of course, I think that was like maybe 20 centimeter in diameter. That's the way they did. So anytime you bend a wire, what you do, you are recycling the magnetic field. So imagine, this wire is like this, and then the current is flowing from negative to positive, and then you can check with the Gauss meter, it shows like 20, 20, 20, 20, 20. But as soon as you turn this like this, you make a loop or you make a U shape, so what happened? You are recycling the magnetic field. And that's amazing, because you know, I loved mechanics. I had to compare this with the turbocharged engines. You know, when you have a muffler and then the gases or everything else goes through the muffler, and you know that fumes, everything, they have a lot of kinetic energy. So like 45 years ago, I think they did this turbocharger. So they had to reuse that, you know, gas coming or everything coming from the muffler, and they reuse it again. So they increased the efficiency by 20-25%, which was amazing. So when I have here 1 millimeter, or I mean maybe like 5 millimeters, it's showing 24. So when I bend that 25 millimeters and I make a loop, so I will have like 50-60 Gauss. So this is exactly what happened. The dipoles, I have to explain something important. Whenever we loop something or whenever we bend something, and then it's current carrying wire, so magnetic field is recycled. So dipoles, like I will explain in a minute, dipoles orientation is reversed in respect to the flow of current or flow of electrons. See, if I do something like this, nothing changed, nothing happened, because the current is flowing from left to right or right to left. It's all arbitrary. It can be from this side or the other side, but like I said, to be more simple for me, I had to use from negative to positive. So those dipoles orientation is reversed with respect to the flow of current. So I had to do this experiment, which is very important experiment. You can see this is called solenoid, and then what I had to do, I had to use 2 loops, I had to use 3 loops, 4 loops, 5 loops, and this is going to be maybe like 100 loops. It doesn't matter. So let me connect this so you can see how important this experiment is. So let's see, that one is also connected. Okay. Now, I'm going to show you with my Gauss meter. When I connect this to 12 volt DC, you can see I can measure the Gauss meter. It must be in the center of this circle. See? Center, 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 all the way. So let me go ahead and connect it so you can see. I'm hoping that you can see my Gauss meter. See, it's showing 65. Can you believe that? It's going 65. Because if I get a higher only, it's going to be only 20. This is going to be 62. I'm hoping this is going to be more. Yeah, 82. So, see, the more wires you have, the more magnetic field is recycled. But Andre Ampere was genius. And he did mention so many times, you know, they have to be tightly wound. And then I have another experiment I show you. If these coils, circles are not close together, because each one of them is like a magnet. So when they're close together, they add up. When they're a little bit farther away, they add up, but not as good as they're close. So you can see this coil, this is the same way, and then it's also acting like a S and N, even though this is like a solenoid, and it does exactly the same thing. So we have like S on this side, and then N on the other side. I have another experiment which will substantiate this. Let me show you. Let me get this one out of the way. Well, of course, I have so many experiments, but I don't want to do all of them because of time and everything else. So we don't have that much time. And this is also amazing experiment, so you can see what I mean. Why Andre Ampere said that they might be tightly wound, And he was absolutely right. He was one of the greatest minds in the history of mankind, I think. History of science, I would say, exactly like Michael Faraday. And you can see here, I have a solenoid, but you know, on purpose, I'm hoping that you can see this part here. And then on purpose, you can see here, I wound those a little bit further. Each one is almost like, you know, half a centimeter away. But see here, they're almost close together. So what happened if we have like 20 coils here, or we have 20 circles here, or 20 turns here, they add up. But here they add up not as good as they add up over here. So I show you, let me connect this to, this is going to be, oh no, it has to be the other way. It has to be this way. Okay. So we got the minus here, and we got the plus the other side. This is the minus. That is the plus. See. That is the plus. So this is very important experiment, you can tell. So what happened? This Gauss meter is an amazing device. If I measure the magnetic field on top here, where the coils are so tightly wound, it shows more magnetic field. When I show over here, it shows less. When I show inside, it's almost like 600% more. You can see even the high school kids know. If you have a coil like this, let me show you if I have one over here. Yes, I think I do. Even the high school kids know. This is just an ordinary coil, you can tell. If I measure the magnetism outside, it's going to be like 14 Gauss. But if I measure inside, it's going to be 110 Gauss. Well, of course, this is not a good coil because I need more turns. And this is the way it is. Always inside, when you bend the wire like this, outside, magnetic field is not as good as outside. Inside. The reason why you are recycling, see? Inside, well, of course, it depends on how small the coil is, how small the turns are. You get more magnetism here. Now I show you on this one, which is so important. Let me get my Gauss meter. And please pay attention here what happened. I'm going to measure here, so it's going to be different. I'm going to measure here where they're not, where a little bit away, where apart from each other, and then I'm going to do also the inside. Okay, so let me see. I'm hoping you can see that. Okay, so I'm going to measure here. It shows only 19 Gauss. It shows here only 2 Gauss. But when I go inside, it shows 65 Gauss. How about here? When I go inside, it shows 80 Gauss. So what happened? Here shows less. The reason why we have less, the magnets are not close together. I had to substantiate this with an experiment, simple experiment. See, I have a bar magnet like this, and normally the bar magnets like this, it doesn't matter how, these are like 25 years old, but still they have a good magnetism. And I remember 25 years ago was like 1000 Gauss, now it's the same thing. So if I have a magnet like this, let me see if I can show you on this Gauss meter. See, showing 1168 Gauss. If I have another magnet, and then it's going to add up. Let me show you. If I have another magnet, it's going to add up. So you got 1,500. So what happened? This is exactly like those wires. If I put something in between, even though they attract each other, but the magnetism is not going to be as good. Let me show you. I have like 1.5 centimeters like a foam in between, and then we can measure to see how different it is. See, it's showing less. The reason why this magnet is not adding up. So that's exactly what happened. If I have like 10, 20 magnets in a row, and then there's nothing in between, like I said, they add up like this, and the end result will be so good. I made a model, so I show you for the, let me put this aside, set this aside, so we can have another experiment. This is so comprehensive, you can tell. Well, of course, I'm going to have to show you, I missed something important. I'm sorry, yes. Any current carrying wires, well, of course, this is a thick wire anyway, and this is a little bit exaggeration. And you can tell, if you have like iron filings all around this is going to show exactly where it's going. Well, of course, it's not going to be this much. It's going to be like maybe 3 or 4 centimeters on each side. It depends on your current, it depends on how thick the wire is. So you can see these are concentric lines, and the reason why it is because of the magnetism. And then this is called current carrying wire. And then I have to get my own idea, and this is so comprehensive, it shows you exactly. So I had to use washers like this. Well, of course, this is an exaggeration, and then it shows exactly when you have a straight wire like this. So what happened, nanometer, we're talking about billions of this, because these are so huge anyway, but at least it shows everything. So I came up with my own idea, and that was a slinky idea. See what happened here? This side, inside, they are closer, outside is more. So if I have a coil like this, what happened? Inside is going to be more magnetic field, outside is going to be less. And this was the one I built, so I'm hoping that you can visualize exactly what I mean by the slinky. Well, of course, I have the slinky over here. You can tell. Well, of course, this is iron. You cannot use this. You have to use copper or anything. So you can see you have small slinky right here, and then you have big slinky right here. And this big slinky, if I measure this outside, it's going to be only 14 Gauss, and then if I measure inside, it's going to be 170 Gauss. Let me see how much this one is. I measured this before. So outside is going to be 11 Gauss, and then inside is going to be 90 Gauss. So imagine that is the reason why all these wires, everything you see is wound. And there's something important I've never seen in any books that mention this. This is extremely important concept. If the wires are wound zigzag fashion like this, it's not going to add up. The reason why, you have to go back to Van Haan's theory. See, this is facing this, it's going to be repulsion, 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 repulsion. But if you do something like this, like the way the coil does, like let me see where that was. I put it in. Yeah, when you go like this, so what happened? This is going to be S facing N, N facing S. So they add up. And then I have some coils I show you. This is so important. But how could I prove this? I had to come up with my own genius idea that, this is the only way I can prove it. So this is a huge coil, and then I remember when I got this coil, it was like 600 Gauss, which is so important, so powerful. So what I did here, I went zigzag, zigzag. So there is no way that is going to add up. The reason why, this is facing the other one, and S is facing S, N is facing S, and then it shows a little bit magnetism, but that's so important. And it doesn't matter how wide they are, how spread they are, it's not going to work. Always when we're dealing with the magnetism, they must be the same direction. And this experiment is extremely important because of separation of charges. Let me set this aside so I can explain this experiment. And then I forgot to mention, I'm sorry, I missed this part. I have like tubes, I have like a copper tube and everything else, and it doesn't matter how big the tubes are. Let me show you. How big the tubes are is going to be always S and N. And even I had to make this my own. This is a square, and my guess was 100% right. When the charges are going, so we got south, north, north, south. And this is the advantage of separation of charges. Okay. And then I had to come up with this. This is a solenoid. It's exactly like this. Few minutes ago I explained. Inside is going to be more magnetism because, like I said, the magnetic field is recycled, but the outside is not recycled. And then I had to do this special experiment. So we have like north and south on this round one, but on this square one, which is exactly connected to this, we have a north, south, south, north. And then I had to do this with a solid also. This took me almost a week to prepare because it's not easy to cut such a huge aluminum. Let me show you. So this is solid aluminum because I couldn't find copper and they're so expensive anyway. So I had to use this. And then I realized this is acting exactly like the way I did it on the others. So we have north and south, and then when we cut this here, charges are going to the sharp points. And it's amazing, after so many years, like 200 years, Benjamin Franklin was right for the lightning rod. Everything is traveling to the sharp points, and he was absolutely right. And he was a great person. I have a great respect for him. So what happened here, like south and north, and then we have north, south, south, north. So if I don't cut this square, this is going to be exactly as south and north. And it doesn't matter how I turn this 360 degrees, it's going to be the same. And that's exactly what happened inside the earth. That's exactly what happened in everything. And my idea was always, if something works in atomic and subatomic level, it can also work in, planetary levels. I remember I had a speech in CU Boulder in Colorado, and then they loved this idea. Some professors came over, they shook hands with me. I said, 1 millimeter wires compared to the 12,000 kilometers Earth is the same way. Because we have on Earth north and south. In a wire we have south and S and N. It's the same thing. But it depends on, everything works in a microscopic level. And then the Earth is the same way. And then after, let me show you if I have this wire, yes. Imagine, when we connect this to 12 volt, let me show you. When you connect this to 12 volts, probably I don't even have that device in less than microsecond is going to be S and N. It depends on, because Michael Faraday shows that electricity is traveling. It depends on how thick the wire is, how much the voltage is, and everything else, how fast. And immediately one side becomes south and the other side becomes S. And this was my idea and my creative mind. I add this up because Lorentz forces are there. So whenever we have this south and north, and then current is going through that, or magnetic field, they are going like a screwdriver. They're going like a, like this screw, and it's going through the Lorentz forces, and that also adds up. This is another one. You're going to love this one because it took me almost a day to do this. This was amazing job. I mean, this was so difficult. So I was comparing Earth with these wires. You may not believe, it took me almost one day to do this. You know how difficult it is? I had to use, I had to get a plastic ball, and then you see I started all the way. But see how good it is? It's tightly wound. And then, let me see, I think I can show you this. When I connect this to 12 volt, you can see the, let me show you. When I connect this, where's the other one? Okay. When I put the compass on it, when I connect this, did you see what happened? Let me show you here. Did you see what happened? So, even though this is a small globe, it is showing exactly what happened on Earth. I remember one year 2000 I had my Earth's electric field, and then I realized that so many people loved it, but unfortunately there was no cooperation whatsoever. They didn't want to help me to publish it, and at that time there was no YouTube anyway. I proved it to the world that that the Earth is a good conductor. And this was German scientist. He was an amazing person. His name was Steinhall. And then they were using thousands of kilometers for the 1800 for the telegraph. And then they had no idea that the Earth is a conductor. Earth is not as good as this wire, of course, but they conduct electricity so good because it is not like an electron conductor, it's a proton conductor. So if you have like a little bit, water, and then you have a soil, and then you put the stick, your voltmeter, it shows like 1 volt. But that 1 volt is not going to light up any lights because of less electrons anyway. So let me get this out of the way so we have more experiment. I think I can show you. And in fact, by year 2004, I did find a globe. It was copper, and there was another one, solid aluminum. But no matter how much I looked online or for Amazon, I could not find less than one, like a 1 inch, which is not going to help me. But this one is good. So it shows that what, it doesn't matter if I connect it from here to here. It doesn't matter. See, this is globe, but it's acting like a small Earth. Everything is interaction of between the dipoles, and then that's what happened. Let me see what else is left here. And then this was the important part. Let me see, I think the important part of my thing is the iron. Oh, no, I'm sorry, I have another one. I'm sorry, I missed this one here. I have another one here. Okay, I have another experiment here. Let me get this out of the way. I used to have a helper here, but now he's not here today. On my by myself, and there's so many things I have to do it myself. It's not easy, it's a small lab. So you can see here, I have wires, and then I did explain in my theories, it doesn't matter if you have the coil clockwise or counterclockwise, everything is going to be the same. So it's going to be S, it's going to be S all the way here, and then this side is going to be N. So I had to use four compasses here, and then this is important experiment. So you can see it doesn't matter how your wire is. See, here is like a spiral, here is different. You see, everything is going to be the same, but you can see everything is in the same direction. It's not zigzag. So let me connect this. This is going to be the plus. This is going to be the minus. Okay. Now this side is going to be the plus. Okay, this side is going to be the plus. So when I connect this, so see what happened. See, all these compasses, let me see if you can see that. Everything is activated. So what I did here, I had clockwise, counterclockwise, clockwise, counterclockwise. So when I have the compass over here, this was counterclockwise, and then if I have the compass over here, that is going to be clockwise, and the other one is going to be counterclockwise. See what happened here. When I turn this on, and this wire is a current carrying, and then when I rotate this, see, nothing is going to change because they follow exactly the same thing. So what it means that the separation of charges are 360 degrees. It's not going to make any difference how you do it, but it's going to be the same. So let me get this out of the way, and I think I have one more experiment, and that is so important that substantiate my idea of separation of charges. Okay. I think this was the last one, but I have one more for the no, I have one more here. I'm sorry, I missed this one. This is a huge thin copper sheet, and then what I did is I connect this to plus and minus, and then what happened when I put my compass over here, we have more charges here. This is, see how big this sheet is? This is almost, I would say maybe 25 centimeter by 50 centimeters. So again, I had N and S. So it doesn't matter as long as you have like a diamagnetic like this copper, it's going to be. But what I did special, I had to cut this like this. So the charges are traveling here, this interaction of the dipoles. And again here, when the place is cut, shows S and N. So it doesn't matter how the charges are, they always rearrange each other, one another, and then they just act exactly like clockwise and counterclockwise, and then shows, okay. Now, this is extremely important concept. Let me show you. I have a press that is like 1 ton press. And imagine charges Well, of course, I have to explain a little bit. See, magnets are amazing. I mean, I had these magnets, some of them more than 24 years, and then I remember wrote in my books and everything else, that nothing has been changed. As long as this iron, this magnet is not facing any iron, it's going to be the same. But if it's facing an iron, after like few years, what happened, they lose a little bit. So you can see the magnetic field on the edges here are more, or when go inside it's going to be less. The reason why the charges from this magnet, which is like 1,500 Gauss, it is showing, let me see if I can do it with the Gauss meter, it shows that inside it's less, but by the so let me see if you can see it here. See, it's showing 338 Gauss. When I go inside, it shows 27 Gauss. When I go here on the side, on the sharp side, it shows 245 Gauss. When I go inside here, it shows 32 Gauss only. So see, it doesn't matter how the charges are. Wow. Okay. And there's another one which is so good, and then you're going to love this because this is so good, and this substantiates my idea 100%. You may not believe this huge magnet is only 1,600 Gauss. I mean, sometimes, if you show to ordinary people, they say, well, it's a huge magnet, it must be more. No, this is exactly as powerful as the small one over there. But this is amazing experiment. And I remember when I did this in CU Boulder, and I had never seen anyone does this, any experiment at all. So you have a magnet over here, and then as you know, from the north to south, and then it's called line of forces, Michael Faraday called, and then we call it flux line. And then my guess was right. When we have an iron like this, the iron is amazing. Metal has the highest energy level per nucleon, especially when we're talking about iron isotope 56, is the highest energy level per nucleon. It's amazing. So imagine when I have a 1,600 Gauss over here, when I measure the magnetic field in the center here, it shows 75. Here it shows 35, here it shows 60, but on the edges shows 125. I was wondering why. Because see, it's interaction of all these dipoles. We're talking about quintillion of dipoles, interaction, and always by the edges we have more. Let me see if I can show you here. I think I can show you. Let me see. So imagine we have like a see, here shows 60, on the edges shows, wow, 240. Amazing. This edge shows 340. See, when we go, this edges is going to be less. It's going to be 220. So this is important idea because, I have to explain this a little bit. This flux line, they have a magnetic dipole moment. So is the electrons, but the electrons is so different, and then I have to explain why. There's only one word for the electron. Why it does have the magnetic dipoles moment. The reason why is intrinsic. Intrinsic means naturally. And I remember Sir Isaac Newton was explaining about the gravity and things like that. It says it's intrinsic. It's exactly like that. Electrons have the same thing, but the difference with the flux line is flux line has a loop. And that's amazing. This goes from north to south, circle and circle and circle, and it's exactly like a speed of light, and it's amazing. It is not going to cut or anyway. That's the reason why you have the induction, and then I will show you in a second that how important this is. I had to use this fluke, which is the most, famous or the best in the market. Is made in Holland or Netherlands, and it's amazing. This is called the clamp meter. I show you. Let me see if I have a magnet over here, round magnet. Or it doesn't matter. I can do it with this magnet as well. So when we put it in this clamp, you can see what happened. When I rotate this easy, see, it is showing 1 ampere. Isn't this amazing? See, half an ampere, a little bit faster, it shows 1 ampere. So the reason why Charles Coulomb said 6.24 charged particle passed from the point is 1 ampere. Ampere said the same thing. We are talking about the quintillion. 6.25 quintillion charges in a second makes 1 ampere. So imagine I'm just rotating this in less than a second, so I get 1 ampere. Let me see if I have more experiment here. Oh yeah, I do. I'm sorry. There's one important experiment left. I have to get up and get that. That is so important. I did this experiment. Let me see if I can post this on the wall so you can see much better. I did this experiment in 2004, and my guess was right. And then when you saw this magnet was showing the same thing, more gas, and then I was thinking, what if I use the iron particles or iron filing? And my guess was right. So I had to cut something like stars like this, and then this is the magnet. Well, of course, it was a bar magnet like this, which is 1000 Gauss. And then I had circle like this. I had like a square like this. I had the spikes like this, and they all shows the same thing. Let me see. I think I have it over here. I can show you. See, I made these spikes like this, and then you can tell here I have 500 Gauss. Magnet like this, or 1000 Gauss, it doesn't matter. Center shows 35 Gauss, here shows 27, on the edges shows 178, 181, and 226. So this substantiates my theory. Charges are separated, and this interaction of between the, dipoles. That's the way what happened. Let me see if I have more. I think I covered everything. I had to use this lead, was exactly the same. Overall, lead is not a good conductor, but again it was showing S and N. I had to use this aluminum, is exactly the same. It was showing S and N. And then I had to use this stainless steel, which is so expensive. I used to work in this company, and this is the only stainless steel it won't rust. And then we used to work in John Crane International Corporation, and we used to use this for the big refineries and things like that. A thing like this maybe cost more than $500 because this is special stainless steel for that corporation, and they won't rust, and then it's amazing, they won't even magnetize. So everything is altered. Molecular, structure is completely altered or manipulated. I have one more experiment. I think this is going to be the end of it, I think. Oh, I'm sorry, I missed this one. You may wonder what this is. You may wonder what this is. This is maybe 10,000 or 20,000 pieces of magnet. Well, of course, everyone knows when you go in a textbook, you can see you are not supposed to hammer any magnet because this lost its magnetism almost like 500%, which is a lot. But still, see, they're holding together. And when I have the compass on this, you can see, let me see if that shows. See? See, compass shows north and south. I just wanted to prove something. It doesn't matter how many magnets you have, millions of millions of millions, it's going to be the same. And well, of course, I have to explain something. This is so important. His name was Wilhelm Weber, and most people don't even know who this person is. He was great scientist, and in fact he was working with Gauss in 1800, this Gauss meter, and Gauss was an amazing person. He was the only one who proved to the world that the magnetism from the Earth from inside, not from the outside, because it was controversy as it's from outside, but he proved it. So Wilhelm came up with the idea that the magnetism has to do with moleculars. And then I was thinking, and then I made a connection with Debye, that great American Dutch scientist. Well, he was born 100% after Mr. Wilhelm Weber. And then he came up with these dipole ideas, and then he got Nobel Prize also. And I remember in Solvay conference, you can see his picture all the way to the end. And Mr. Debye proved that. And then when I made the connection, I said, Mr. Weber was right. So this is molecular. So what happened? Domain theory is the new one, and most books don't even mention Mr. Wilhelm Weber. So that's what he did. And then I'm guessing I have to do another theory next time when I'm talking about Mr. Weber, and then what he did for the magnetism. And he was amazing scientist, and it was like 1800, and then he used to work with Mr. Gauss. And this is another thing, I did not mention, I'm sorry, I missed this one. Overall, any magnet like this, the reason why I know, because I bought this Gauss meter. Without the Gauss meter, you won't be able to tell. It's always, it doesn't matter, we have one magnet, two magnets, 100 magnets back to back, always in the center we have less. But on the edges we have more. The reason why charges are interacting with each other and they push, like charges, and then that's what happened. And finally they settle, and there's no other place to go, so they concentrate on this. So exactly the same thing happened on the coil. Solenoid. Exactly the same thing. Let me check this out. See, if you measure the magnetic field, on the side, see, this side is 75 and the other side is 65. It's two layers of bonding. If you go like on the top right there, it shows 10 Gauss. But if you go inside, it's going to be 75. The reason why, like I said, magnetic field is what? Is like recycled. And I think that's all for today, and I appreciate your support. I'm hoping if you like that, you can just subscribe my channel, and then I appreciate your help. And you guys always make me work hard and then come up with more theories, and that is so amazing. And then one more thing I did not mention, this is so important, and I'm hoping this is going to be the end one. I came up, this is my invention. You can see this is a coil. It has 1000 Gauss. Can you believe? But see how good it is. But one amazing thing I discovered, if you go back a year and then watch my electric motor, and unfortunately he wanted $60,000-$70,000 I did not pay, to do mass production and things like that. I did not pay because I wasn't sure. I did not trust them. See, if you have if you connect this to 12 volt, both shows N. But imagine when I turn this side, even though the flow of current is not changed, but this is going to be S. The reason why, the dipole's orientation is reversed with respect to the flow of current. And I use this same concept for my electric motors, and then it was great success, and then so many people emailed me, they loved it. But I'm hoping one day if I do this, and then that's going to be breakthrough in science. The reason why my electric motor is not using commutator, is using Lorentz forces. But unfortunately, I'm not going to invest $100,000 because I'm not in Las Vegas. I'm not going to gamble, and then I just gave up. And like I said, this is a good idea. You can see what I mean by this. So the current flows from the same thing. It's going to be N and N. But when you rotate this, even though I'm not changing the flow of current, but this is going to be this. So I use this concept for my electric motor. I used 1, 2, 3, 4, and then guess what? I had in my electric motor 12,000 RPM. How could you have a prototype 12,000 RPM? Like I said, if you want, you can watch that electric motor, which was published, I think, a year ago. Thank you very much for watching, and then I'm hoping you learned a lot today. I'm sorry I could not cover everything because it's not easy. So thanks a lot, and then I hope to see you in a month, and this time it's going to be for the superconductivity. It's going to be a little bit more complicated, but I'm hoping after that it's going to be how to visualize Michael Faraday's line of forces. That's going to be also a little bit complicated. Thank you very much for watching, and then you guys are a big supporter, and then I love you guys. Anytime you have any question, you can email me, vahandavudyan@aol.com. I'll be happy even to come to your place and then explain everything. If you have any university or college, I'll be happy to pay all expenses by myself, even the colleges or high schools. I'll be happy to do that. The reason why I want to promote the science, so want to activate the sense of wonders in the young generation. Thanks a lot for watching, and appreciate it.